Now that we've done our acceleration lab, we have collected our position data. As we saw this thing rolling down the track, we saw that these points were getting farther and farther apart. So I want to start us off here to where velocity is a vector. A vector meaning that it has a direction and a magnitude. A magnitude, that's where we're just going to get into a number. But we're going to see that this velocity is a vector and that this acceleration is also going to be a vector. So what I mean by that is it has a direction. So if I take this position point and I just put all these position points down below, so that way I can draw in a velocity vector. If I draw in a velocity vector going from this point to this point and I draw it halfway, then that would be this acceleration or this velocity vector. I'm showing the direction that it's going to the right, and I can see then this velocity has this certain amount. And then if I go to this next point, I can draw in a velocity vector halfway about to the second point, and I see that this arrow here has to get bigger in order to reach this arrow. So over this time, the velocity went from this small value to a larger value. And the only way that happens is if I add more arrow to it, meaning that there's this acceleration going to the right. So if I take this arrow, add it on to this one here, I get this one. And then this velocity vector is also going to increase as I go out to the next point. I have it now getting even bigger, and the only way that happens is if this velocity vector has an acceleration vector. So if I take this arrow and put it to the end over here, then I would get this vector that I have over here. So what we're seeing in this acceleration lab is that this acceleration should have been relatively constant. So my arrows here for my acceleration are pretty much the same length, but my velocity here is changing. So I'm seeing that this position versus time is changing because my velocity is changing. My velocity here is increasing. So as we get to a position versus time graph, I know that in our car lab last week when we had this position versus time, we were able to derive this equation, this x equals to v naught times t plus x naught, and we were able to do that with that y equals mx plus b last week. Now I see that position versus time graph, and it doesn't look linear, but I do know from last week that the slope of this graph is my velocity. So I know the slope of my position versus time graph is my velocity. Last week we went through the area getting x times t, and that didn't give us anything, but the slope does tell me the velocity. And I see that as I start off at the very initial point in time, it looks like this is a zero slope, and then as I move on to a later point in time, it gets to be more positive, and then a later more point in time, I get even more positive, then a later point in time, I have it even more positive. So my slope initially is going to start off with a zero slope. So over here it has a zero slope. So it starts off at a zero slope and then it increases to a positive slope because the slope is this velocity. I have this positive slope here at the end, so that means I start off with a zero velocity and it becomes a positive velocity. And we can see that the direction of it is to the right, and the velocity vector shows that it's increasing as well, showing at first like a relatively small or zero and then increasing in this velocity vector. So last week when we looked at our equations, on this equation sheet we have this x equal to x naught plus v naught times t plus this 1/2 at squared. And so this is this equation that we're seeing here. Now last week there was this linear because this term was not included. Now we're seeing that this graph here should look like this parabola because of this t squared dependence. So this equation that we're going to use is this x equal to 1/2 a t squared plus v naught times t plus x naught. And so I like to rearrange my equation to match that. If you like writing it like how it's written on this equation sheet, then do so. I like using this format where this v naught is my initial velocity, the x naught is the initial position, this a is this acceleration, and t is time, telling us this position of where it is. So this is this equation that we are able to get. We can derive this equation. It's not essential for us to derive this equation from here. But as we see these different points with a zero slope, we should have a zero velocity. And then if I increase to a later point in time, I should have a more positive slope, giving me a more positive velocity. Now I can just go up to this positive point. And as I get to a later point in time, I should have an even more positive velocity because I have a steeper slope. And then later on, I should have an even bigger positive velocity because I have a steeper slope, giving me this graph that we should see where the velocity is constantly increasing over time. Now we see this linear relationship. Since we have a linear relationship with this graph, we can use our y-axis equals to slope times x-axis plus the starting. So this is just the way that I write y equals mx plus b. So I use what's on the y-axis, and in this case, on the y-axis, we have v for velocity. So we have this v on the y-axis, and it's going to equal to the slope, where we don't necessarily know what the slope is, but we're seeing that this velocity is changing over time, and we do know that when velocity changes over time, that has to be this acceleration. So the slope is this acceleration, a. And on the x-axis, we have this time, t. So a times t plus the starting for the y-axis, where the starting y-axis is going to be the initial velocity, and we write this as v0, or the velocity at time equal to 0. And we call it v naught or v sub 0. If you like writing it as v sub I as initial velocity, sometimes that also helps. But now we have this v equals to a times t plus v naught. So if I bring up our equation sheet, that's this one here. This v equals to this v sub x 0 plus a sub x times t. And what they're doing with this subscript, this is talking about one dimension. So we only had this thing rolling down the track, down this x direction. It didn't fly up in the y direction, it only went in the x direction. So we can talk about velocity in this x direction. So now we have this equation that I'll write neater as this v equals to a times t plus v naught. So with any graph, we can talk about the slope or the area. So in this case, for this graph, the slope, which is change in y-axis, right? So change in y-axis divided by the change in the x-axis. So that's going to be velocity, change in velocity over a change in time, change in y-axis over change in x-axis. That is going to be our acceleration. So our acceleration here is this change in v over change in t. So So our acceleration is that slope. So our acceleration is the slope of this velocity versus time graph. We can also get the area. This is definitely something that will be asked about. So when we get area, we take the whatever's on the x-axis times the y-axis. So x-axis times y-axis. So on this graph, on the x-axis, we have time, and on the y-axis, we have velocity. So the area here is going to be velocity times time. And I'll change this right here. Y-axis times x-axis. So velocity times time. Now if I pull my equation sheet, I know from last week that velocity times time gave us this position. And if I were to move this x naught over to here, make it x minus x naught, that's that displacement, then x minus x naught equals the velocity times time. And since we're taking into account how this velocity that's accelerating with this component right here, then this velocity times time is like taking this whole thing right here of this a times t plus v naught. If we take the area of this entire graph. So if we take the area of this entire graph, then that's going to tell us our displacement. So the slope of this graph tells us our acceleration. The area tells us our displacement. Displacement, once again, that's how far from where you start. So we can ask how far from the start, that's that displacement. So we can get the area of this, which is taking into account our average velocity and time to get this displacement. And we did that by getting the area. So the last thing for this lab that I wanted us to get to was taking this graph, and I wanted us to plot it versus this t squared. If we plotted it versus the t squared, we should see that we get a linearized graph. It should form something of a straight line. And that's because this equation that we have, this x equal to 1/2 a t squared plus v naught times t plus that x naught. And that's this equation from our equation sheet where I have this x equal to x naught v sub x naught times t plus 1/2 at squared. I just get rid of the subscripts x because I know I'm talking about the x direction. With this, since we are plotting this graph versus t squared, this is now on our x-axis. So the t squared is now on the x-axis, where the position is on the y-axis, leaving us with y equals to mx plus b. So on this graph, we could also get the acceleration if we know the position and the time squared. We can get the acceleration because we have our m being 1/2 the acceleration. So our slope here, if we were to get the slope of this graph, which would be the change in position over the change in t squared, the slope of this is going to equal to 1/2 the acceleration. So if you get this acceleration, it's going to be 2 times slope. Now, I want to take us to some example questions. As I start us off on this one, we see that we have an object that travels along a straight line and a horizontal surface. Its motion is described by this velocity versus time graph shown in the figure. Which of the following methods will determine the total displacement? So what we're trying to get is the total displacement of the object between 0 seconds and 5 seconds. So I do know already that to get with a velocity versus time, I can get the area. I can get the area for this graph. Looks like it goes out to 5 seconds to 10 meters per second. So I could get this displacement by doing 1/2 base times height, where the area then would be 1/2 5 seconds times 10 meters per second, which would be 1/2 of 5 times 5. So this would be about 25 meters. 5 times 5, which would be 25 meters. And I got that by getting the area. Another way that we can do it, this is by using this average speed. Now the average speed, so this V average equals the total distance divided by the total time. Now we're trying to get the displacement here. So it looks like this only has a positive horizontal velocity. So we can definitely take this V average times the time. So this V average times it by the time. That'll give us to this total distance. And so I would look at this, it goes 10 meters per second plus starting of 0 meters per second divided by 2 to get the average, multiplied by the time of 5 seconds. So 10 plus 0 divided by 2, that's 5 times 5. So I get 25 meters once again. To another example question. We have a velocity versus time graph, and we have a student that's going to drop a rock from a cliff such that the rock falls downward towards Earth's surface in the absence of air resistance. The downward direction is considered to be positive direction. So they're saying that there's a rock and it's falling off the edge of this cliff, and they're saying that this way is positive, and so this rock is going to fall and fall and fall and fall. So I know the velocity is going to be getting bigger and bigger as it starts to fall. And you see it here graphically that it's getting bigger and bigger as it's falling in the positive direction. So the graph is showing us this function of time, and it's asking us which of the following methods should be used to determine the total distance that the rock travels after 4 seconds. So we do know a couple different ways. If we were to take the average speed, it looks like it goes up to about 40 in 4 seconds. So starts at 0, goes up to 40, so it goes 20 meters per second on average for 4 seconds. So that's one way. Another way is finding the area, but let's see what we have here. Using the maximum value of the curve as it states that the rock traveled 40 meters in 1 second. That's not gonna be true because it's changing. It goes 40 meters per second at this last point, but at another point, it's going 10 meters per second at 1 second. So it doesn't keep that same rate. So it cannot be this right here. You cannot use the maximum value of this curve because the velocity is changing. Now I do know I can use the area of the curve. If I get the area, then I'll be able to get this displacement. I know the area tells me that displacement. The slope of the curve is an acceleration. So the acceleration is the slope, and that's not 10 meters per second. So in 1 second, the slope would actually be, if it goes up 10 meters per second in 1 second, the slope would actually be 10 meters per second squared. So it did travel 10 meters per second in 1 second, but it doesn't travel 40 meters in total because there's this acceleration. So they gave the wrong units here for acceleration, which is the slope. So that tells me also that letter C would be wrong. And the answer can be determined because we did by using the area.